are talking about homework from last night, and one of the easier ones you said was?
The derivative of 8 to the x.
Okay. And so you did what with it?
Well, I know that the answer is going to be 8 ln 8.
8 to the x ln 8.
Yes, yes.
Yeah.
But I don't understand why that is, like how I got it.
Okay. So let's take a look at what we did then yesterday. Let me make sure we did e to the x 2 days ago, right? And generalized exponentials yesterday, right? Making sure that, yep, okay, good. So, there are two ways that I could get to the derivative of 8 to the x. One of them requires logs, which I'm going to talk about today, and one of them requires rewriting 8 to the x as an exponential e to the x. So fundamentally, we have defined b to the x as e to the x ln b. That's just what it is. So now if you simply take the derivative in this form, you get y prime is equal to e to the x ln 8 times the derivative of the inside, which is ln 8.
And then e to the x ln 8 is just 8.
Right.
Because I tried to take the ln of both sides because I knew you can do that.
Yeah.
And I ended up with, just ln 8 and not 8 to the x.
Yeah. Let's
So that's
skip ahead to Friday and pretend that we know something about logs. If we don't, let's pretend we do. If we know something about logs, then we can take the natural log of both sides and use log properties to rewrite this as x ln 8. And now if we take a derivative with respect to x on each side, we get 1 over y times y prime is equal to the derivative of x times the constant ln 8. And so therefore y prime is equal to ln 8 times y, which is 8 to the x minus.
Oh, I see.
And it's
Because I got, but I didn't know how to do them.
yeah. So for now, I'm not asking you to do any of the logarithmic differentiation, but just to use the form that we have.
Okay,
And
because
go.
where I knew you could do e to the x of ln 8, but I don't know, something got, it just makes sense.
Okay.
And now.
Good. Anybody else have questions? Yes.
So, B to Y is C.
Okay.
The question was about finding the maximum rate.
The maximum height,
Rate
maximum rate.
with this equation.
So P of t is equal to, and this is the rate of spread of something nasty, right?
Yeah.
And the K-grid is on day 3 of cold, so we covered our viruses and white cells. So
4 minus P.
what's that?
4 minus P.
Is it 4 minus t? Before we get into this problem, let's try to understand a little bit what's going on with it. And when I try to understand an equation mathematically to map it to the real world, I start looking at values. And so I look at P of 0, and P of 0 would be 300 over 1 plus 2 to the 4th. And I would try to look at P of infinity, which is really the limit as t goes to infinity of P of t. A physicist would write that, a mathematician would write that. And when I do that, then I would get 2 to the negative infinity down here as my form, which is 0. And that would give me 300. So what I can see is that my it appears as if whatever it is spreading from a value of 300 over 17, which is going to be a little bit less than 15, a little bit more than 15, to a maximum value of 300. And so my graph is going to look something like this. And so I'm looking for the point where the maximum rate of change is occurring. And that maximum rate of change is going to occur when the derivative has its max value, or when the second derivative is 0. So you computed p prime of t, and what did you get for p prime of t?
Plus 2 to the 4 minus p times ln 2 over 1 plus 2 to the 4 minus p over times 300.
Okay. And so we have a double negative going on here because p of t is in fact equal to 300 times 1 plus 2 to the 4 minus t to the negative 1 power. And so that allows me to do negative 1 here times derivative, and I get a negative 1 from the change over there. So that's good. Okay, now the question is, how do I maximize this function? We don't know a lot about maximizing this yet, so we're not going to do this in a calculus sense. But if I were to think about it algebraically, I've got a fraction. How do I make that fraction as large as possible? Make the denominator as small as possible, or make the numerator as large as possible. What I find that's interesting is that this quantity, 2 to the 4 minus t, is big and obnoxious and it gets in my way. So I'm going to make it get out of my way by calling it x. I'm going to substitute x for that. And now what I'm looking at is x over 1 plus x squared times a bunch of constants. And I'm going to maximize this quantity when I find the value of x that will maximize that fraction. Okay, so let me get a sense of what the graph of this fraction looks like. It's clearly going to have x equals negative 1 as an asymptote, and it's going to go through 0. And it looks also like it's going to have a horizontal asymptote of y equals 0. And that means that it has to go up and then come back down here, and it's going to have a max somewhere right there. So where is that point? Any ideas? Are you allowed to use a calculator?
So
Well,
I use calculator, but
yeah.
I don't know how to write and get
No, we don't need to worry about it. I mean, we could use the second derivative to do that, but let's just focus on maximizing this with our calculator.
x equals 0? Yeah.
X equals 0 is clearly not it, right? Did you see how I got the quick sketch there? Is that one? Okay, good. Sleep mode. Y equals, clear, wish I had a clear all. X divided by square. There. And we're going to grab that guy. And here he goes down that way, up that way. And it's a little hard to see. I think there's a max there. Let's take a closer look. By setting my y min to -2. my y max to positive 2, graph it. There it goes again. Hey, there's our max. Hi, max. And now, if I do second calc, would you look at that? Option 4, maximum. And now I can set a left bound of 0, and a right bound of, looks like 2 will do. And then for my guess, I'll just hit enter. And there's my max when x is equal to 1. And if x is equal to 1, then that means that 2 to the 4 minus t is equal to 1. And 2 to the 4 minus t is equal to 1. That means that 4 minus t is equal to 0. Therefore, t is equal to 2. That's it. Did you notice this move right here where I substituted something simpler for my complicated and repeated thing? That's a common move in mathematics, where we take something hard and we say, this is ugly, let's call it x. We did that a lot in Algebra 1 going on. We said, this is unknown, let me call it x. That's the spirit of algebra. Here we do, this is ugly, let me call it x. Better? Okay, good. I had an interesting question that was originally going to be a Quizlet question, but we're just going to make it an interesting question. So we're going to do this as a fake quiz in your notes. Go. Going to wrap up a couple of different ideas that you've played with. All of them or some?
I agree. Two, so like a
She didn't know what she was trying to do.
she's like lost the game and started thinking.
Yeah. Who is the other lost soul?
This one is right.
Oh, yeah. He's another one who's just kind of like, when you get to T-Fade, it'll be better.
Oh, yeah, she's good.
Now you're using inverses here, and that's okay-ish, but can you do it without appealing to laws?
Yeah.
In other words, by
Oh,
inspection.
just, oh, okay.
Yeah.
Oh, oh.
I just want you to use what you know already.
Yeah.
We will get to laws.
I just
today.
realized that.
I don't disapprove. It's good math that you do. I want you to get there another way. Charlie, what's F inverse of 1?
0.
All right. Because 2 0 is 1. So here you had to reverse engineer. You had to ask yourself, what x value would give me 1 when I plug in? Using that idea, what is F inverse of 4, Philip? Exactly, same reason. 2 squared is equal. And now the $62 question. What is F inverse prime of 4? What do you say, John?
1/4.
That's it. Using our inverse function theorem, 1/f prime of F inverse of 4. I can do that for a second there. And F prime is equal to 2 to the x ln 2. And F inverse of 2 is equal to 2, of 4 is equal to 2. And so I get this guy right here, using the inverse function theorem. Good, very good. All right, speaking of inverses, let's talk about the inverse of e to the x. First of all, is e to the x invertible? Is it a one-to-one function? When I take a look at the graph and when I take a look at the derivative, I see that the derivative is always positive for all x's, which means that f is always increasing, which means that it has an inverse on the entire real line. I think I've mentioned this before, but I'll make it more clear now in case I hadn't. And that is that a function that is always increasing or always decreasing is called a monotonic function. And intuitively, I think we understand that a monotonic function must be one-to-one because if two x's are different, then their f of x values must be different as well. And that is what it is to be one-to-one. We'll actually prove this in the next chapter. Monotonic implies one-to-one, which implies that the inverse exists. Okay. Now, what can we say about this inverse? Well, let's see. What would the graph of the inverse look like? We know we have to reflect about the line y equals x. Do your best sketch of that graph. Better now?
Yeah.
And hopefully your sketch looks something like this. Let's identify the features of this inverse by looking at the features of the original graph here. Notice that the original graph of e to the x has a horizontal asymptote y equals 0. And we can identify 2 points. We could identify any 2 points we wanted to, but the easiest point to identify is 0, 1. And the next easiest point to identify is 1, e. And so between these and the horizontal asymptote, we have 3 points. And we can do a 3-point solution for our inverse. We have a vertical asymptote, x equals 0. We have the graph going through the point 1, 0. And we have the graph, whoop, I overdid it, there it is. We have the graph going through the point e, 1. Bless you. Notice, I've sort of implied it, but I've never directly stated it. Notice that when I draw that line y equals x, I can find matching points by doing a perpendicular across and going out the same distance. So that the line y equals x is always the perpendicular bisector of the 2 points, the matching points a comma b and b comma a. All right, so we've got our graph right here. And what can we say about it? Well, let's say the following things. For f of x equals e to the x, it has these properties. First, it has the property that the domain, what is the domain of f of x equals e to the x? A set of allowable x values. Good. Which is also pronounced all real numbers. Please do not use the abominable ARN. And how about the range of, what's that?
Over 0 to
0 to infinity. And in fact, this is open here because we have the horizontal asymptote that is not crossed. How do I know that the range can't include any negative numbers? Well, if I go back to the limit as n goes to infinity of 1 plus x over n to the n power, it's entirely possible that I could put in a negative value for x, right? But as n goes to infinity, that negative value for x will be swamped by n, because n will continue to grow, go out to infinity, so that at some point, all of these fractions will become positive for this quantity here will become positive. Does that make sense to everybody? In other words, for all x's, the limit as n goes to infinity of 1 plus x over n is equal to 1, which means that for large enough values of n, 1 plus x over n has got to be in the neighborhood of 1. It's got to be a positive value. So I can never get negative values out of e to the x, hence my domain range. Now let's invert all that by simply swapping domain and range. F inverse of x, which we are going to call the natural logarithm, sometimes called the Naperian logarithm. So actually Ln was not discovered by Euler, but was discovered by Napier, interestingly, before Euler ever came along. It's sort of a strange tale. The domain of this will be the range of the original, and the range will be the domain of the original. And you can see that from the graph here, that the domain is all numbers greater than 0, and the range is everything. Interestingly and strangely, the negative portion of the range occurs in the domain portion 0 to 1. So all of the numbers from 0 down to negative infinity are packed into just that little small area 0 to 1. And in fact, the natural log here, like this, is a model for what happens with black holes. As you go in closer physically towards the center of that black hole, time slows down more and more and more, so that you end up with, the closer you go, the longer it takes you to move further, which is really strange kind of thing. And then out to here. How would I take this limit right here and invert it? What is the statement of this limit for the inverse? You can answer that either from the graph or the limit as x goes to 0. That's very good. But we have to do one thing to make sure that we obey the domain.
Okay, then it has to be
Yes.
so coming from the right frame.
Nicely done. Good job. So this is the inverse statement of that right there. And only because our domain is restricted. Just like so. Excellent. All right, well, what about the algebra of natural log of x? I would like to submit that the properties of natural log are going to imitate the properties of the exponential. Remember, we have three exponential properties: the addition, the subtraction, and the power rule. And so for the natural log, we're going to have three corresponding properties. The natural log of a times b is equal to the natural log of a plus the natural log of b. And the proof involves inverting. And it's fairly simple. We're going to let a equal e to the x for some x, and we're going to let b equal e to the y for some y. So that x is the natural log of a, and y is the natural log of b. So if a and b are e to the x and e to the y, then substituting into the natural log of ab, I get natural log of e to the x, e to the y. And now using my exponential property, this is the same as natural log of e to the x plus y. And because the functions are inverses, they cancel. And I get x plus y, and x is ln a, and y is ln b, and we are done. In a similar kind of argument that I shall not bore you with, I could show you that natural log of a over b is natural log a minus natural log b. And finally, that natural log of a to the m is equal to m times ln a. And so these are the power properties. Excuse me, these are the log properties for natural log. And what we have to do is to resist the temptation to try to do anything silly like distribute the log. Every student tries that. And in particular, you got to watch this one closely. There are going to be a lot of students that want to rewrite this as ln a divided by ln b, which is going to be, as we'll see tomorrow, actually a completely different thing. ln a over ln b is going to turn out to be a change of base formula for us. So watch that carefully. I did something here that I skipped over something that I wanted to be really explicit about. I said here that f of x equals e to the x and f inverse of x is equal to ln x. And because of that, one of the important pieces of algebra for the natural log is just its inverse property. And that is that e to the x and its inverse cancel each other, giving x back. Because we define natural log as the inverse. And so these four together are the way in which we are going to solve logarithmic equations. So for example, exponential equations. So for example, suppose I have 2 to the x equals 3 times 4 to the x, and I wish to solve for x. Well, there's a number of things that I could do with this. For example, I could divide both sides by 4 to the x. That works. Or, let's do it in that way first, and then we'll come back and do it in a slightly different way. If I divide both sides by 4 to the x so that I can get all of my x's on both sides, then I can appeal to exponent properties here and find out that 1/2 to the x is equal to 3. So that the natural log of 1/2 to the x equals the natural log of 3. And now using my exponent property, I get this solution right here. So the algebra of natural log is used to solve exponential equations. Usually, exponential equations will have more than one solution path because the log properties are very flexible and useful. Let me show you. What if I began this equation by taking the natural log of both sides? Well, on the left-hand side, I would get x times ln2 using my power property. On the right-hand side, I observe that I have first a product, so that I get ln3 plus ln4 to the x, which is equal to ln3 plus x ln4. And now what has happened is that my log properties have reduced an equation that was multiplication and exponentiation into an equation that is multiplication and addition. In other words, if you think about repeated operations as being levels, repeated addition is multiplication, repeated multiplication is exponentiation, the logs take all of those down one level and make it possible to solve. So, now I can collect like terms here and here and get x times ln2 minus ln4 is equal to ln3, and therefore x is equal to ln3 over ln2 minus ln4. Wait a second. That's not what I got back here, or is it? Aha! Using my log properties one more time, I get ln2 fourths, which is ln1 half. And these are the same. Because there is often more than one solution path for exponential equations, therefore, there will possibly be more than one form. In fact, I could do this a little bit differently and write this as ln of 1 minus ln of 2, and ln of 1 is 0. So that a fully simplified answer might look something like that. So you just have to watch for different possible forms. If your answer doesn't match the one in the back of the book exactly, fear not. Work at it with some log properties and see if it can transform into the right answer. And notice that I'm resisting the temptation to try to simplify this because I don't have any property that will let me do that at this time. What's that? ln of 2 is going to be less than 1 because ln of e is 1 exactly. It means 2.7. All right. The calculus of natural log. This part, in some sense, is the easiest. We can accomplish it one of two ways, just like we accomplished the derivatives of inverse trig functions one of two ways. And those two ways were either using the inverse function theorem or using implicit differentiation. If you're getting the idea that implicit differentiation can be used to circumvent the inverse function theorem, you are correct every single time. Every solution involving inverse function theorem can also be done with implicit differentiation. The setup for I of t is that we're going to consider the natural log to be the inverse of some function, and the parent function is the inverse of course, e to the x. And therefore, f inverse prime is equal to 1 over f prime of f inverse. And so we need to calculate f prime of x, which is e to the x. And we need to evaluate that at f inverse, which is ln x. But hey, look, e to the ln x is automatically 1 over x, and we're done. Poof. Isn't that nice? This is my favorite inverse function theorem because it just comes out so easily. The same kind of thing happens over here with implicit differentiation. if y is equal to ln x and I'm seeking dy dx, then I can get rid of my function with an unknown derivative by applying the inverse to both sides. And now if I differentiate with respect to x on both sides, I get e to the y times dy dx is equal to 1. And dy dx is equal to, therefore, 1 over e to the y, which is x. And we're done. The interesting question is, which of these is, quote, better? What do you think? Which one do you like better? You like the one on the side? Show of hands. How many of you like the one in blue? And how many of you like the one in black? And how many of you don't have hands? Or are you equal? You're deciding. Okay. Good. Talk out loud, please. What are the factors?
You have to give it the first one.
You like the one in black? Yeah, I'm actually somewhat ambivalent myself. I like this because I can think of it in a straightforward algebraic kind of way. You know what I'm saying? What I like about this is that it's clean, but the cost is that I have to mess with that initial assumption different. And I always felt a little nervous about that. Once I realized that both of these are saying the same thing in slightly different ways, what that really did for me is it helped me understand the assumption theorem more better. So in the end, I would probably, if I had to do something like this in the wild, boy, what would I do? I'd probably do it like this, but this still has an old school attraction for me. So there it is. Let's do one practice problem and we'll call it a day. Something like this. Nope, wrong. There. This is what we're going to do. One possibility is to take the derivative directly. The derivative of natural log is 1 over blah, 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 times the derivative of the inside. See, I can do that. But it strikes me as a waste of resources because I would end up having to use quotient. So instead, I'm going to use log properties to rewrite my division problem as a subtraction problem. I like that. The first one is automatic. The second one is going to give me 1 over x squared plus 1 times the derivative of the inside, which is going to give me 2x on the top and x squared plus 1 on the bottom. Just like that. So the use of log properties is extremely, extremely recommended. Here's an interesting thing that shows up in some of your homework, in one of your homework questions. The derivative of the natural log of kx. Find that derivative. Yeah.
Is it kx?
That's kx. Great, thank you. If you can stack into one small pile, would be very good. Yeah, you can just cross stack.
I think it's somewhere still.
Well, at least it's better than it was, so thank you.
What's the answer?
What is the answer? Why? Yes, if I use chain rule, then I get 1 over x. Did anybody do this a different way? What do you got?
I separate the answer.
Yeah.
I got the same answer.
Mm-hmm. What is the derivative of natural log k? 0, because it's a constant. Yes. And there it is. C log